Hey class, today we're going to be doing section 4.5, which is exponential growth and decay application problems, so modeling our data. So first we're going to start by reviewing, and I know I say reviewing even though it looks different, it's not. The mathematical model for exponential growth or decay is given by this formula here. Now, the reason I said that this is review is because this is the same as A equals PE to the RT. They just use different letters. I don't care which letters you use, as long as you know how to apply it to different situations. So usually we use P for principal amount in an interest rate problem, R is interest rate. So here they're just kind of switching our letters, as instead of P, it's A sub 0. So that sub 0 just means initial in math, so our initial A value. And then E to the K, instead of R, they use K as our growth, a constant growth rate. So instead of interest rate, it's growth rate, or decay rate if it's negative. All right, and then T, again, is the amount of time. So if K is positive, we've got a growth function. If K is negative, we have a decay function. Let's look at an example. Again, I don't care which letters you use in the formula, as long as you use the formula properly. Example 1, the graph below shows the US population in millions for 5 select years from 1970 through 2010. In 1970, the population was 203.3 million. By 2010, it had grown to 308.7 million. Find an exponential model for the data. So they want us to come up with the exponential model so we could use it to find population in different years. So first, how many years has that been? Well, from 1970 to 2010, we have 40 years. And I know that, so if I'm using, and I'm going to use the new letters here, just so we can see them. So A initial is going to be this one, A sub 0, because in 1970, that was our population. So that was our initial population. This one is going to be A after 40 years. So if I plug those things in, I have 308.7 equals 203.3. And now these are in millions of dollars. I just had to remember that. And as long as they're both in millions, you've got that equal units, you're fine. You can't do it if only one of the values is in millions and the other one's not. And then E to the K times 40 up in the exponent. So after 40 years, now my goal is to solve for K and then rewrite my model, which is the equation. So when they ask for a model, they're looking for that equation. So solving for this, we already talked about solving exponential functions in the previous lesson. So if you missed that one, go back and look at that first. So the first thing I'm going to do is I'm going to isolate the exponential piece by dividing both sides by this multiplication factor. I end up with 1.5184. Use a bunch of decimals. That way you don't end up with a rounding error. 4 decimals is usually good. All right, and then from here, the exponential piece is isolated, so I'm going to change it to log form. Now remember, a log base E of something is the same as the ln of that something, and we can use the ln button. So whenever we have a base of E, we want to use that ln. So I'm going to change this to the ln of 40, the ln of 1.5184 equals 40K. So remember, the log is the exponent, so the exponent goes on the other side of the equal sign. All right, and then I could divide both sides by 40, use my calculator, and I get K is, let's see, we have the ln of 1.5184 divided by 40, and I get 0.01044. I know that's 5 decimals, but that's all right. Doesn't hurt anyone. So our exponential model is A equals A sub 0 E to the 0.0104 T. Or if you put A equals, what was our 203.3 E to the 0.0104 T, that's also fine. Just note that T is years since 1970, because I'm using that 1970 amount as my initial value there. I actually kind of like this one better. If we think about our functions, if we write an equation, usually we have like f of x equals blah, 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 blah with an x involved. So this is like a of t equals blah, 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 blah with a t involved. So remember, e is a number, it's not a variable. So it's kind of nice to see the whole equation with just the variable t and everything else kind of filled in. Now, using this model that we came up with, which year will the US population reach 335 million? So now I can use this to figure this out. 335 equals 203.3 e to the 0.0104 t, and then solve for t. So the steps are going to be identical to what we did last time. First, I'm going to isolate the exponential piece. I get 1.6478 equals e to the 0.0104 t. Then I'm going to change to log form. ln of 1.6478 equals 0.0104 t. Divide by 0.0104 on both sides. I know I'm going fast because I don't want the video to be really, really long. All right, and then ln of 1.6478 divided by 0.0104 ends up as 48.02, so approximately 48 years, but read the question carefully. It didn't say how many years. It said by which year. So now I need to take and add that to 1970, and I get, let's see, plus 1970, I get 2018, about 2018. All right, so there's our first example. Next page, we have a HalfLife example here. HalfLife is super cool. The half-life of a substance is the time it takes, or that's required for half of a given sample to disintegrate. The half-life formula, I don't want you guys to use a new formula. I want you to use the same formula as we were doing, or A equals P e to the RT if that's easier for you. The half-life formula isn't any different than this one. It might look different, and we'll see what happens, but I really want you to understand what that formula is coming from, and it's based from this one. So let's just use this. So we have carbon-14 dating, the Dead Sea Scrolls, so cool. Use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. So this is the half-life amount. So if it says, what's the half-life? It's 5,715 years. Now, I want to find a model. So again, I want to find the equation with just a t in there. So I need to solve for k using our formula. So a equals a sub 0 e to the kt. Now, I don't know what it started with. I'm going to leave a blank for a second. So I have e to the k times 5715 years. And then I know that whatever I did start with, a sub 0, after that amount of time, what I'm going to end with is half of a sub 0, or a sub 0 divided by 2. We don't actually need to know what a sub 0 was, because my very first step in solving this is dividing both sides, just like we did in our last examples, dividing both sides by a sub 0, and it cancels out. So I end up with just 1/2 equals e to the k times 5715 power. So that's how we set this up. I do want to see that step where your a sub 0's cancel out. Don't just jump to the 1/2 equals e. I want to see all these steps. It's really important to communicate why you had this formula with a 1/2 equals e to the kt. All right, so now I'm going to change this to log form. ln of 1/2 equals 5715k divide by 5715. And I get k is approximately negative 0.00012. When there's lots of zeros, you want to definitely include enough decimals after the zeros stop. So my formula, A of t, is going to be some sort of initial value. And in this case, I don't know what that initial value is. So I'm just going to leave it as a sub 0. E to the negative 0.00012 t. And remember, it's decaying. After 5,715 years, it has decayed to half the original amount. So as time increases, it's a decay model, which is why our k value is negative. Now we can use this to solve for part B. Now, I would strongly suggest you pause the video now and try B on your own. See if you can do it after those examples that we've done together. In 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. So we can use math to estimate how old stuff is. Super cool. Math and science. Yay. All right. So again, I'm not sure how much we started with. So I'm just going to have an a sub 0. E to the negative 0.0000. Nope, that's too many zeros. 3 zeros and a 1, 2. T. Okay, I'm estimating the age, so I'm finding T. Given that when we found the thing, I mean, that was 1947 when we found it, but that's not how old it was, right? It's been there for a while. So there was 76% of the original. So remember, 76% of a number is that number times 0.76. So notice I'm not using the half-life information anymore. I'm not using the 5,715 years because I'm not looking for half. I'm looking for how many years it's been if I end up with 76%, not 50%. So our first step, again, is to divide by a sub 0. Those end up canceling. 0.76 equals e to this number, t. Now change it to log form. So the ln of 0.76 equals negative 0.00012 t. Divide by this k value. And t is approximately 2286.97. Now remember, that's years since when? Well, that's how many years it had been when they found it in 1947. Well, it's 2020 right now. So now how old would they be? Which is super cool. So then how many years has it been since, let's see, 2020 minus 1947. So 2020 minus 1947. Now, if you're watching this video years from now, make sure to adjust. That's 73 years that we need to then add to this value. So 2288, I'm just going to say approximately 2287 years because it was almost that long, plus 73. 2287 plus 73 is approximately 2360 years old. That is super old. So cool. All right, and that's it for today's lesson.